Okay, so this is where we left off last Tuesday. We were saying that in order to determine a scene, these are the important components of a virtual scene, and one of them was we just started creating this file. Let me open it in Notepad++. So this is our scene file. We just say that in our virtual world there are two spheres located, centered at 3, 3, 3. One of them is centered at 3, 3 with a radius of 4. It's a blue sphere. The other is at, oh, by the way, did I start recording? Yeah. The other is at 6 minus 4, 8. This is the center, the coordinate of its center with a radius of 3, and that was a red sphere. So this, first we have objects in our scene. That was the first component. The second component was the camera. And the camera actually is composed of some extrinsic parameters and some intrinsic parameters. Like extrinsic parameters means that for example, where the camera is located currently. Because one of the things that you can provide dynamism, one way to provide dynamism in your scene is to have your camera move around. So that, for example, you can have a fly-through of a scene, fly over a scene, and things like that. And the way you change where the camera is located is camera center position, and the center position has another importance in perspective view. This is the point where all the light rays converge. So this is like the focal point of our camera. This is in other words, we treat the focal point of the camera as the camera center location, and we have a gaze where the camera is looking at. And the up vector also fixes the camera at a specific location with a specific direction and orientation. So these are like the extrinsic parameters. The other thing is the camera comes with an image plane. And there is also dynamism that which can change in image plane. For example, when you want to zoom in, we didn't talk about this last Tuesday when we were talking about the field of view. So here in the slide, let me also show you. So we talked about field of view angle, how much of the scene we are going to be seeing by setting up the window boundaries. So we have an image plane, which is a plane parallel. So a plane, when I say image plane, it's an infinite plane extending in all directions. And which is parallel to the XY plane of our camera reference frame. But the image window itself has boundaries, and these boundaries are usually given to us symmetric to our gaze, which means that we are going to assume that our gaze hits the center of this image window, and to the left and to the right we have equal amount of pixels. So like it's basically a symmetric field of view. In the horizontal field of view is symmetric, and similarly our vertical field of view is also symmetric, where the top boundary and bottom boundary are equally distant away from the center. So one way to increase the field of view is obviously to increase the boundary of the image window, right? I mean, if I make this 4, 8, I will be seeing a larger piece of the scene. Another thing that actually real cameras employ is to change this distance d. So let me use a different color. So this image is a lot of, it's very crowded. Lots of things on this image since we did it. We edit lots of things while we were discussing. So right now, if you just look at this image as from scratch, this is the first time you see this. It looks really crowded, just a mess. But yeah, I'm going to talk about these again. So if you look at this D, which was the distance of the image window from the camera focal point E. So this distance was given as 2 in this example. And let's see what will happen if I play with this distance. If I change this distance, what happens? And this is actually what real cameras do when they are doing what? I was just going to give you a hint about what happens when you move this D close to the, for example, let's see what will happen. If you reduce D, instead of D being 2, Exactly, zooming. So when I reduce D, so that's the correct answer. So I was just about to say this is what the cameras use to zoom in and out. So when you reduce D, so the image plane gets closer to you. Do you think we're zooming in or zooming out? Yeah, this is like a trick question. It seems like you're making the scene closer to you, like it seems like it's zooming in, right? But actually, it's zooming out. If you think about it a little bit more carefully, you're going to see that when decreasing the D is going to increase our field of view. So we are going to see more of the scene. So, but the image, when your image in terms of its resolution, don't worry about it. So it's, I mean, it's actually it's very common. I would also say zoom in because you're getting the scene closer. But yeah, if you think about it, your image resolution stays the same. It's always a 2000 by 1000 image. So your image size is not getting, it's not getting larger. Here, when we get this D. 1, your image is still a 2000 by 1000 image. Okay, so it's not enlarged. The image window, it's still from -4 to 4, it's still -2 to 2. So image size is the same. What happens when we get the image window closer to our cells? So what happens is that we, if you look at the boundaries are going to have a larger angle. If this D is closer, the field of view angle is going to get larger, which means that you're going to be seeing, it's like you have this small window, you're moving, just imagine you're seeing the whole world with this small window and you're getting this window closer to you, you're seeing more of the world within that same window size. Which means that if you just focus on the image you get on that window, actually you're zooming out. Here you're seeing more of the scene, which means you're zooming out. Zooming in requires you to move the image window away from you. And you may now see the reason behind why we have these, for example, sports photographers. If you want a really large optical zoom, you should have a telescopic lens, right? It's like it's the same effect as you need to be able to move this image window away from the focal point as much as our field of view is not constant. We can by playing with D, by changing D. So for a fixed D and the fixed boundaries, our field of view is going to be constant. But zooming in and zooming out is actually the process of changing our field of view. So when you're zooming in a particular object, imagine you move your window closer to that object which was at the center of your scene. For example, imagine there's a small sphere here. You're moving this window closer to the sphere, and the image window is, so what will happen is that this small sphere is going to occupy more space on your image. So that's why it's like you're zooming in on this. But when you're zooming in, what you're doing is you're decreasing your field of view. Some objects that are at the periphery, for example, when you're moving your image window closer to this object here will cease to be within your field of view and you won't see it anymore. So for zooming in, we increase D. So, field of view is decreased in zooming in. So when we are zooming in, field of view is decreased. So, and if considering this distance, when this distance increases, you can actually look at this. Just try to compute the angle here. So let's try to visualize our field of view. It's always good to visualize these things from either side view or top view because we are looking at a 2D projection here. Exactly, same like checking the room from a keyhole. If you move yourself close to the keyhole, you can see more of the room. If you view it far away, you see smaller of the room, a small part of the room. So let's take a look at it from the top. So imagine this is my image window with a fixed length, and this is where that E is. We are looking at it from the top, and this is my horizontal field of view angle. So the horizontal field of view angle is sometimes given by this angle, I think, or sometimes by the whole angle. I mean, if it's saying, for example, 60 degrees, it probably refers to the entire angle here as the 60-degree field of view. Okay, so if this is 60 degrees, imagine what will happen if I move this image window closer to the eye point without changing anything else. So this is, they have the exact same length. Okay, my image boundaries stay the same. Now look what happened. You see, look at this angle. It's larger, right? Which means that, and if you look at how you extend these rays, how these rays extend towards infinity, which objects, which part of the, so this red one obviously sees more of the scene, but it's still on the same size image window, but a larger area. So decreasing, so this is the distance D from E to the image window, this distance, we call it D. As you can see, it's when it decreases, the field of view enlarges. There is one singularity point, for example, for fish eye vision, we cannot have this angle 180 degrees because that's a singularity point. There will be no projection. So what I mean is that 180 degree field of horizontal field of view corresponds to a distance of D is equal to 0. It's like you see, you have infinite horizontal field of view, like 180 degrees field of view. Usually, even in OpenGL, for example, they don't allow this singular point parameter. They start, for example, the field of view at 179 degrees or so. We cannot have it exactly equal to this, but even 179 field of view angle sees their entire scene on one image, which makes it like a fish eye viewing. So the field of view is larger. So playing with this D, we can have actually a variable dynamic field of view angle. All right. So that's one thing to discuss about these parameters, what happens when we change this D. So when you're setting up these parameters, it's good to know what happens. So given with these parameters, for example, we have a scene description here. We can actually compute with these given values, we can actually compute our field of view angle, right? With some trigonometry, we would be able to compute the field of view angle. So how it would do that? So let's see. What is, so distance to I is 2 units, and minus 4, 4, minus 2, 2. So actually, if you look at our setup from the top, so let's get a new window. So from the top, since this distance D is 2, actually it's, let me write it a little bit shorter than that. So this is 2, and this is minus 4, and don't forget this minus 4 is given in the local coordinate reference frame of the camera, where this is x is equal to 0, and this is like, it just shows the boundaries. It's not the coordinates in the world coordinate system. So now, what is this angle here? How can we find this? This is 4, this is 2. It is tangent, arctangent 2, right? Yeah, exactly, arctangent 4/2. So let's write it in Google. Arctangent 4/2, which is 2. 1.1 radians. I want to see it in degrees. So the radians are, for example, pi is 90 degrees, okay? 2 pi is 180 degrees. In radians, pi is, we have to multiply by 180 and divide by, there's, pi is involved here. So yeah, either 180 over pi, something like that. So yeah, so let's write this one. Oops. Probably there's in degrees, radians in degrees. So it's 63 degrees, 63. So we have a very large horizontal field of view, almost 125 degrees in total. So this angle was 63 degrees. So the horizontal field of view angle, field of view angle horizontal is somewhere around 126 degrees. So we are seeing this much. So we can actually compute this, as you can see. And as you can see, if we increase this, for example, if you do the same thing, if the distance was 4, it will be 45 degrees, right? Arctangent 1 is 45 degrees. So if you increase this distance from 2 to 4, if d is now equal to 4, field of view angle, horizontal field of view angle is going to be reduced from 126 to 90 degrees as you move it. So we can decrease the field of view by increasing this distance. And the effect will be zooming in a particular object that is in the field of view. That is at the center or that is in the field. Because while if we do that, some of the objects, as we see here, are no longer going to be visible. For example, if there's an object here, in this large field of view, it's visible in this image, but it's not going to be visible as we decrease our field of view. So that makes sense. Okay, now, last time we were talking about how we can compute. So our first job in the ray tracing geometry is to find the center of the pixel on this a particular pixel, which is identified by two pixel coordinates I and j, which are given to us in integer coordinates. So our pixels, if the resolution is given as 2000 by 1000, we call them, I think, on the slides nx and ny. So nx is so we are given an image nx by ny. So this is 2000 by 1000. So depending on whether you're going to start your indices at 0 or 1, I mean, if you start at 0, your I is going to be changing from 0 to nx minus 1, right? Our largest pixel coordinate will be nx minus 1 if nx is 2000. So just like zero-base indexing in C arrays or in other many of the programming languages. And so here we also need to have some conventions, for example, saying where is 0, 0? Okay, in this pixel, is this pixel the 0, 0 pixel, or is this one the 0, 0? Where is my 0, 0 pixel? Is it the top left or bottom left? This is just a convention. It's usually somewhere on the left because we usually increase the x-coordinate from left to right, but the convention regarding whether it's bottom down or top to bottom or bottom to up, how the pixel coordinates are going to changes from system to system. For example, on our monitors, I think the bottom left corner is considered as 0, 0, and your mouse coordinates, for example, if you get the mouse click location, it's probably using a coordinate system in which bottom left is 0, 0, or maybe it's the other way around. But the way we have our local coordinate reference frame defined, this up vector, it's 0, 0 is here, so the y coordinates are actually increasing as we move from bottom to top. But just bear in mind that sometimes we may need to do reversal of the y-axis to convert between these two coordinate systems. Okay, so if this part is 0, 0, for example, we need to compensate for it. So let's see how on the slides what that pixel coordinate is to be consistent with the slides. So let's see, yeah, 0, 0 is actually the top left one. So we are on par with, we are on the same page with the slides. So 0, 0 is here. So it's like reverse of how our up vector is, right? So we are going to take into account that. But our first job is given ij compute the pixel coordinates of any particular pixel. With those pixel coordinates, we are going to generate a ray equation, and with that ray equation, we will be able to do intersection tests easily. So first job is to get this ray. And you had your recitation yesterday. Probably you must have seen parametric line equations. Did you talk about parametric line equations yesterday? And vectors, cross products, things like that, I'm sure it was covered. So parametric line equations too. Perfect. So, but an intuitive, not a better, but an intuitive way to view line equations in 3D is any line has a starting point. Okay, we need a starting point and a direction to indicate a line equation. Okay, so and we can parameterize this. So if you start from this, go in this direction. This is what a line is written. So in other words, for example, any point on the line could be written in this parametric form, where t is going to indicate where you are. So this is going to be your unique address given this reference point, where you say, I'm going to start from here. I will go in D direction, and I will go in the D direction t units. Multiply d by t. So this is just, everything here in this equation is just vector algebra. Scaling a vector, d is a vector. The direction in 3 dimensions is indicated by a 3-dimensional vector like this, which basically tells you that how fast you're going. So this vector, direction vector, does not indicate a position. It's just a direction. Okay, it's just saying you're going this fast in the x direction, this fast in the y direction, and this fast in the z direction. So this is a vector. And since this t is a scalar, this is just a scalar vector multiplication, and this is addition of 2 vectors. The result will be px, py, pz, another vector, which shows you where you are on this line. So a parameter t will indicate where we are on the line. So let's now derive the equations that will help us to find the pixel coordinates. So now I'm going to have a clean slide, and let's see how we can do that. In our case, in the example we have, we are lucky because this u vector and the v vector, the x-axis and the up vector of the camera aligns with the actual XYZ world coordinates. But in general, they don't need to be aligned. For example, I may have a camera which looks at the scene sideways. Okay, so an increase in V, for example, may actually, so which means that your image here is also sideways. Okay, moving the camera like this is like moving the entire image window also sideways. The image window can be arbitrarily oriented. Let me get myself a piece of paper to as a reference to an image plane. So you may actually have the image plane tilted, and the pixels, as you move in a row on this image from left to right, as you can see, your x coordinates your x coordinates may not be increasing. It really depends on what these, oh, by the way, you should have corrected me, this u and v vector, in our case, in our example, so this was u, this was v, okay, the up vector is v, and this is w, this is our local coordinate reference frame. So u is the x-axis, local x-axis of the camera system. This is how we indicate the u vector. So we were given the gaze, which we assume it's like hits the center of this, and we are given the value d, so gaze vector is given. And now, if we can find an equation which can tell us for any ij pixel value, what are the pixel px, py, pz values in the world coordinate system, then I can form my line from E to this px, py, pz. In other words, my direction d will simply be p minus whatever this px, py, pz is, which let me call it p, the center of the pixel, p minus e if I have this vector subtraction here, p minus e, what will it give you? It will give you the direction from e to p, right? And then after that, your ray equation, ray t, will simply be equal to e plus dt, where d is this p minus e. So the only thing that remains is to find this. So how can we find it? The derivation on the slides proceed in stages. First of all, what we have here is each pixel. So for example, if we knew the coordinate of 0, 0 here, or similarly, if we know where we hit this center of the plane, what is the coordinate of the center of the plane, we can do that. And one way to do is for example, here, if you know this point P, actually I know which point I intersect the center of this image plane, right? I mean, it's actually, if you start from E, go in the gaze direction, d units. D is your distance in units, right? So your t, your parameter t, could be in the same units as your whatever your unit is in this world coordinate system. So look at this. If I start at E, go in the gaze direction, d units. D was the distance between I and the image plane. Where will I end up? I will end up exactly at this, if it's symmetric, I will end up at the center of my image window, right? So what do we call here on this slide the center of this? So here is how we compute that actually. We call this point M, okay? So it's written here. So if you look at the first equation, that's the simplest. G, very good point. So G has to be normalized. It has to be unit length so that going D units in that direction will correctly leave us at the center. That's a perfect point. So when you are, usually when you're using these directions, sometimes we will have these directions normalized. They're just, if you just want them to indicate direction and we want to go in that direction a certain number of units, they have to be normalized. So in our case, our gaze was 0, 0, minus 1, and it was normalized. Its length is 1 unit. If you give, for example, the gaze as a non-normal vector like 0, 0, minus 3, it's also a gaze in the same direction. If you go with this much in this direction, so vectors also have like quantities in them, so in magnitude. So if also it indicates how fast you go in the z direction, you won't, if you just multiply it with d, it will not be going d units. Okay, so for them to be a single unit, it has to be normalized. So if we find g as an arbitrary vector, one thing we have to do is divide it by its length to normalize g. And this is really important. Thank you, Selim, for bringing this up. So we have to, most of the time when we are using these vectors, there's direction vectors. And in our parameter line equations, if we want these t parameter to indicate the same unit in our world coordinate system, g has to be normalized. So in other words, m is equal to e plus gd. So this is what we call m. Now, let's see what we need to do. In order to, so this boundary L is given to us in terms of, L is given as a negative number to indicate the left boundary, right? So L here is a negative number. Don't forget about this, okay? So it's like a coordinate, -4 coordinate. So if I go, now, imagine now I'm at M. What will happen if I start at M and go in the U direction, L units? Okay? Look at this equation, M plus UL. So U is this direction, right? U is basically U is telling you that how does your coordinate change if you're in a row of this image, if you're currently in a row, in a scan line, or in a horizontally. When you're moving horizontally on your image, this is what U is. This is the importance of U and V, and the fact that our image plane is parallel to the UV plane of the camera comes into picture here. U actually shows you the direction of your image window, saying that how moving horizontally on the image, what is that direction? That direction is U, moving horizontally to the right on the image. So if this is your image, for example, if you're moving on a line like this horizontally, the left to right direction, that's U, and it's a unit vector as well. Okay, now look at this equation. It's just again like a parametric line equation, m plus ul. So what does m plus ul mean? L, don't forget, it's the left boundary, which is given as a negative number. So it's not an absolute distance. L is not a distance. L is given to us as the boundary, left boundary, which is always going to be given. If in a symmetric case, it will be some negative value. So m plus u times L will get you directly at this left edge of the image window. So, okay, so going in the U direction, L units. Now, if I was going in the U direction, R units, so by the way, this L, R, B, and T are the values, the variable names we will be using for left, right, bottom, and top boundaries of our image window. So if I do this, m plus u r, going in the U direction R units, I will find myself here on this at this edge, at the middle of my image window. But if you do it with L, since L is a negative number, you're going to find yourself L units, so it's like multiplying U in the reverse, just reversing our direction and going the distance of L to the left. This is basically what it means. So you're going to find yourself here. Now, they are not linked directly. They are like local x-coordinates boundaries for the image window. L and R are x-coordinates of the local reference frame of our camera. So L is like L minus 4, meaning that the left boundary of the image plane is at x is equal to minus 4. It's like the x-coordinate boundary of the image window. So it's not, they can be negative. They are not, L also is not a point, it's a scalar. Okay, it's given to you as minus 4. L is equal to minus 4. What it means is that the left boundary passes through the vertical line x is equal to 4. X is equal to minus 4. Just you can think about this L is equal to minus 4 as this constant minus 4 here. It tells you that your left boundary, your image windows, so your image window is in an image plane. In that image plane, x is equal to minus 4, which is, by the way, this x is equal to minus 4 is given in the local coordinate system where this is 0, 0, 0. And this is the x-axis, this is the y-axis, and this is the z-axis. So this is, it's just an equation of the line. So that's why it's given as, so my left boundary is at x is equal to minus 4, my right boundary is at x is equal to 4. You may ask, if we are always talking about symmetric things, why do we give two values L and R, right? I mean, just say that the width of the image is 8 units long. If it's 8 units long, then it's minus 4 to 4, obviously, right? But this is given as 4 different values to make it generic, so that you may also have some non-symmetric image windows in which you have a gaze. I mean, you may cut the left-hand part. I mean, if the left boundary is at minus 2 and right boundary is at 4, this doesn't mean that you're not still intersecting at 90-degree angle. You can still have 90-degree angle image window, and the left part is cut short here, the boundary. So we may have non-symmetric image windows, but I think in all the assignments we have, in all the inputs we have, you're always going to have symmetric left and right boundary and bottom and top boundaries. So But to make it, just leave it as generic as possible. 4 different values are given. Okay. Now, if I'm at this point, so m plus u times L is exactly this point. Now, my next goal will be to move to this top corner so that I can find the coordinate of the 0, 0 pixel. First, let's first find this top one. So in which direction you have to, so let's call this point, let's name this point, let's call it some variable, like which variable I did not use. Yeah, it's going to be we are going to add another plus vt. Perfect. So it's actually, is it going to be tv time, is it d? Actually it's not t, right? Oh yeah, exactly, t. So sorry, you're right, t is the top. Exactly, I have to go whatever the top boundary is. From this point, I need to go in the v direction, exactly t units, where v is again a normalized vector. So, in other words, if you do this m plus ul plus vt, what does this give you? It gives you the coordinate of the top left of your image window. But is it the coordinate of the center of the pixel? No, right? I mean, we still have to move a little bit to the right and a little bit down to get to the center. How much I need to go? Now, the next thing we are going to do is to figure out, this is not actually, so this is the first one, half of the pixel. Yeah, half the pixel. So half the pixel width. So what is half pixel width? My half pixel width, how many pixels I have here? 2000 pixels in the row. So 2000 divided by L, divided by R minus L. So what is R minus L? The difference between R minus L is the width of my image window, right? I mean, if you do it for R values, 4 minus 4, it's going to be 8. So 2000 divided by this is my pixel width. So I need to go half pixel width, which means that I need to divide this value, or I need to multiply this by another 1/2. So this is the value you have to go in which direction? To the right. So should I add this to the x-coordinate of the pixel value? No, going to the right. Oh yeah, you're right. Actually, I did the computation correct. The half pixel width, actually the entire width is R minus L. I need to do it. Thank you for the correction. So dividing by 2000, I have 2000 pixels. So this is 1 pixel width. And if you multiply it again with 2, which will give you half pixel width. So in which direction you have to go half pixel width so that you move to this point here? Again, you have to go in the u direction, right? We are also going to multiply. So going horizontally right on the image window means you have to always go in the direction of u. Exactly. And the other is minus v. So you got that perfectly right. So this, in order to, after you go half pixel to the right, if you want to go half pixel down, and going down is the minus v direction. So, and what is the pixel height? Half pixel height is going to be t minus b divided by 1000 or divided by ny. And if you multiply this 1/2, this is my pixel height multiplied with minus v. You will go this and add this to your final value. If you add all those things up, I mean, if you add these two things to this m plus ul plus vt, you got yourself your 0, 0 pixel. Now, what about an arbitrary INJ? I mean, if you got our 0, 0, it doesn't, it's not difficult to go, for example, what if in the first row you want to, what if, for example, I is equal to 300 and j is equal to 0? I mean, it means that you're in the first row. All you need to do is, whatever this was, so this was for pixel 0, you need to go half pixel width. For pixel index at 1, how many pixels, what is the distance you have to go? 1.5 pixel width. So this was our half pixel width. If you just multiply this with, so this is half for I is equal to 1, it will be 1.5. For I is equal to 2, it will be 2.5. So I need to add to this I times the pixel width. So add to this what R minus L. So whatever this value here is, I also, without dividing it with 1 over 2, so I times R minus L divided by 2000. Okay, if I add to that, so these are in parentheses before multiplying with U, and you can actually work out the math to simplify this. Oh, there's in both of them contains, if you take this in R minus L divided by 2000 parentheses and call it some variable, call it your pixel width. So it's like in pixel width parentheses, it is I plus 0.5. Okay, I plus 0.5. So this is not US, this is 0.5. I plus 0.5 pixel width multiplied by U. You know how much you have to go to the right for a particular pixel at coordinate I is equal to, for example, I is equal to some value. Do the same thing for pixel height and you're done. So we have finished our first part of the code. We are able to generate the pixel coordinate, center of the pixel coordinate by just doing simple vector algebra. It's all, as you can see, while we were driving this, all we used was the parametric line equation, and we went there step by step. A very good question. Is it guaranteed that the pixel is always square, or can it be rectangular? Actually, it can be rectangular if our aspect, no, it's not about the aspect ratio. It's about if the aspect ratio of the boundaries, for example, our boundaries from -2 to 2 and -4 to 4, the aspect ratio matched exactly the resolution 2000 by 1000, right? In that case, they will be square. If these two aspect ratios do not match, our pixels may be rectangles. But we don't care about those. This equation, this generic equation that we have, our pixel height and pixel width may be different, and we take care of that actually with these equations. The resulting effect would be, and if the aspect ratio of your resolution and the aspect ratio of your window in your virtual world do not match, it will have some stretching or squishing effect. Your image, since in our images, when we display them on our screen, that 2000 by 1000 image, it's not the entire image is a rectangle, but when we are viewing it on our hardware, when we are viewing a PPM image or PNG image, we display them as the square pixels. Okay, so if in real life if in this window they are not square, they will. If there's a difference between aspect ratio, it's, as I said, it will have an effect of whether you're stretching or squishing, stretching in different direction or squishing in one direction. It will have that kind of an effect. So in order not to have this effect, you may be extra careful to have the image window here and your resolution match exactly your aspect ratios. The width over height should match in both cases. All right. I hope this answers your question. So let's take a look at this. What do we have here? So it looks like a different equation, more complicated. But is it really like that? Let's see. First of all, Q is the center. Q is this top left corner. Let me zoom in a little bit on this. Look at this Q. Q is the top left of the image window, which is not equal to our center pixel. So Q is found exactly as we did it. Okay, L times U plus T times V. What we did was, since L was negative, we go left and we add to that VT. So this is how we found Q. But we said something else in our, did we say something to the top left? No, we didn't give any name to that. But then from Q, here it says from Q you have to go this much amount. So SU and SV are the units. How many units? They are scalars. Okay, so SU and SV are two scalars that we computed, that we got these parentheses. So SU, for example, here corresponds to this value that we compute here before multiplying with U. I times R minus L divided by 2000 and R minus L divided by 2000 times 1 over 2. So this is, we use this, how many units we need to go to the right, in the U direction, so we get to the center of pixel I. So this was that value, right? So this one is called SU on the slide. So the number of units you have to go to the distance you have to go from the left of the, so it's just a scalar value so that you arrive at the center of this. So you have to go U in the U direction, SU units, so that you arrive at the center of this one. And also you have to go SV units in the minus V direction. So we also work this out. So SU and SV here, oh, actually this is the equations for SU and SV, we already got them correct, right? I mean, this was I times 1 over 2. We got into parentheses of this R minus L divided by NX. We divided by 2000. This was 2000 in our case. So R minus L divided by NX is the pixel width. We can call this pixel width. So half pixel width plus I. So if I is equal to 1, 1.5 pixel width away. So this is what SU and SV is. We also worked that out on the slides. So although these formulas look complex, we know how to derive them. And the final thing is we need to go SU and SV, but they are not enough. We need to add to this. Okay. So oh here, yeah, right here. The final thing, which S here, which we called P on our whiteboard here. The center of the pixel. The center of the pixel is labeled as S here. Okay, so S is equal to, from Q, you need to go SU units in the U direction and my SV units in the minus V direction. So this is the final equation we got, and it's exactly the same as what we found on our whiteboard. Now, so this becomes the center of the pixel, and our ray equation is simply E plus SE minus E T. Now, this direction, now let's, before I finish today, I was hoping to, I mean, I'm going extremely slow in this lecture, but if you understand all these derivations, it means that all the time we have spent is worthwhile. I can speed up if you want, but hopefully we are going to do some coding next week since we are out of time again today. But something before we finish today, I want to talk about some interesting thing about this direction D. Now, do we normalize this? Do we need to normalize this direction? Or if we leave it like this, what will it mean in terms of T? Look at this equation. Ray equation, E plus dt. So this is D. So if D is as non-normalized, if you leave D to be S minus E is this entire large vector. Okay, so this large vector here, which is probably not normal, which means that its magnitude is greater than 1, most probably. So this is our D vector. It's a vector. Now there are some variable clashes again. D was the distance, right? Don't confuse this distance D, which was a scalar, with this vector D here, which is the direction from this E to the center of the pixel. Okay, so this is a vector D. Now, if this D vector is left as is without normalizing it, exactly. So this was the answer I was looking for. So at parameter t is equal to 0, we will be at the I location. At parameter t is equal to 1, when t is equal to 1, we will be exactly at the pixel. So this is what it means. I mean, if d is this, if the magnitude of d is this, if you make t is equal to 1, you will find yourself here. So as the parameter t changes from 0 to 1, you are inside the camera. So if this is your image plane, that is the front of the camera. For example, if you want to assume that I only see the objects that are in front of the camera, and this is my camera window that is in front. If you treat this entire system as your camera, okay, so if you treat this entire thing as your camera, this is like inside of your camera, right? So when we do object ray intersection, one thing we may require is that in order to be able to see the objects, they need to be in front of the camera. If there's a sphere, for example, here inside the camera, I don't want to see it. So that I will be only interested in intersections where t is greater than 1, okay, or greater than or equal to 1. So you just need to be careful about when you don't normalize, what happens, what are the effects of this on your calculations, what happens when t is equal to 1. So that's a very good point. When t is equal to 1, we will be at point S, right at our image plane. You may also say that, I mean, if there's a sphere inside my camera, I also want to see it. If you do that, you don't need to have this. But what about you find an object intersection in which t intersection point occurs at t is equal to -5. What does it mean? It means that that object that your ray intersects with is behind the camera, right? So obviously you don't want to see behind your eyes, behind your head. So you want to see whatever you have in front of you in the direction of your gaze. So this is very important. These parameters t will be the main things that we're going to decide when we're discussing whether how far that object is from the eye point, how many units, or it's not how many units is going to be far away, it's like how many direction units is going to be far away. But since we're just going to compare the values, it will not, the unit, whether you normalize this d or not, will not matter that much. All right, so that's it from me today. So what we did was, again, to summarize, we just finished the first part. We now know how to generate a ray equation for any pixel. Given the pixel values ij, we're just going to plug them here. So in terms of coding, all we need to do is write two equations, write a function which gets these two i's, r, l, nx, ny. All of them are in our scene file. They are here. This is L, R, B, T, NX, NY, everything is here. This is D, so just plug them here. This is the D, we have the gaze vector, the eye point, so we just plug them into our function, find the coordinates of our pixel, and generate our ray. And the next step will be, if we have this ray, for example, in order to view those two spheres, what do we need to do? We need to say whether this ray is intersecting with this sphere or not. There's a sphere here. Does this ray intersect with this sphere? Or if there's another sphere in front of this one, does this ray, the ray intersects with the sphere? It also intersects with the other sphere. Which intersection is closer to us? And we are going to be doing these things next week. All right, so that's it for today. Cumhuriyet Bayramınız kutlu olsun. Yarın için Happy Republic Holiday to Turkish citizens, and have a nice weekend. See you all next week on Tuesday. Bye-bye. I will stop recording now. Bye.